Quasi-hereditary algebras, lecture 2, standard and costandard modules. Let us start with the definition of a trace. Let A be a finite-dimensional, associative, and unital algebra of an algebraically closed field K. Let M and N be two finite-dimensional A modules. Definition. The trace of M in N, usually denoted trace of sub M of N, is the submodule of N given by the sum of the images of all possible homomorphisms from M to N. Note that this sum is not a direct sum, it's just the sum. Or alternatively, one can say that the submodule which is generated by the images of all possible homomorphisms from the module M to the module N. For example, the trace of the zero module in any module N is 0. Second example, the trace of the left regular module A in any module N coincides with the target module N. That's because for any element V in N, there is a unique homomorphism from the regular module A to N, which sends the identity element in A to V. That's exactly the free property of the left regular A module. And so every element of N definitely belongs to the image of some homomorphism from the left regular module A to N. We will be especially interested in traces which start from a projective module. So let P be a projective A module. The question which we want to answer is what is the trace of this projective module P in some module N. In order to answer this question, let us denote by X the set of all simple A modules which appear in the top of the module P. In other words, a module L, a simple module L, belongs to X if and only if the space of A homomorphisms from P to L is non-zero. For any A module K, let us denote by K sub X the minimum submodule of K, which has the property that for any simple module L in X, the multiplicity of L in K equals the multiplicity of L in Kx. So K sub X is generated by all simple subquotients of K, which correspond to simple modules which are in X. Note that from this it follows that the quotient of K by K sub X doesn't have any simples from X as subquotients. So for any L in X, the multiplicity of L in K modulo Kx is 0. Moreover, Kx is the minimum submodule of K with this property. We just take the intersection of all submodules K with that property. Now we formulate a proposition. The trace of the module P in any module N is equal to N sub X. Let us now prove this proposition. Let L be a module in X and E a primitive idempotent in A which doesn't kill the module L, so EL is non-zero. Then we have the indecomposable projective module A times E, and this module is a direct summand of P, because E doesn't kill some simple in X. If V is an element in some module N, such that EV is equal to V, then we have a morphism from AE, and hence also from our projective module P, where AE is a direct summand, to our module N, which sends E to V. That's exactly the universal property of the projective module AE. In other words, En belongs to the trace of P in N. So the submodule generated by all these ENs belongs to this trace as well, because the trace contains everything what is generated by any subset. That submodule clearly contains an X by definition. On the other hand, any simple in the top of this submodule clearly belongs to X, because we are looking by something which is generated by En, Therefore, this submodule really coincides with n sub x, and that proves our proposition. Here is an example. Let A be the path algebra of the following quiver. We have three vertices, 1, 2, and 3, and two arrows, from 1 to 2 and from 3 to 2. Here are the indecomposable projective A modules. We have the projective module P1, which has stop at the vertex 1, and then we have all arrows which start from 1. We have an arrow from 2, and that's it. So it's also one-dimensional at 2, and the arrow from 1 to 2 is given by the identity map. And this module is zero-dimensional at 3. The module P2 coincides with the simple module L2 because there are no arrows coming out. And the module P3 starts at 3, so it's one-dimensional at 3, and then we have an arrow to 2, so it's also one-dimensional at 2, and the arrow between these two is the identity map, and it's zero-dimensional at 1. Now let's take as n the indecomposable injective module I2. So this module terminates at 2, and then we go against the arrows. We have an arrow from 1 to 2, so it's one-dimensional at 1 with the identity morphism representing this arrow, and we have an arrow from 3 to 2, so it's one-dimensional at 3, and we have the identity morphism representing this arrow. Then we can compute the following traces of P1, P2, and P1 plus P3 in the module n. The trace of P1 is generated by the simple at the vertex 1. So if you start from the vertex 1 in n and generate the submodule, we get vertex 1, and via this arrow also vertex 2. So the submodule is actually P1. That's a submodule of n, and that's a trace of P1 in n. The trace of P2, we start from the vertex 2 and we generate the submodule, but this vertex is a socle of I2, so the trace of P2 in n is just the socle L2. The trace of P3 in n is computed similarly to the trace of P1. We start with the third vertex, it generates also the second vertex via this arrow, so actually P3 is the trace of P3 in n, and it's a submodule of n. And finally, the trace of P1 plus P3 in n is equal to n, because we have to take P1, this gives us the submodule P1, as we computed here, and then we take P3, this gives us the submodule P3 in n, as we computed here. And now if we add them up, it's a usual sum, not a direct sum, we will get exactly n. So the trace of P1 plus P3 in n is equal to n. Now we can define our main notion for today, and that's the notion of standard module. Let A be a finite dimensional K algebra. Let L1, L2, and so on Ln be a full and irredundant set of representatives of isomorphism classes of simple A modules. When we have written these simple modules in this way, we also have fixed the linear order on the set of representatives of isomorphism classes of simple A modules. So we no longer treat them as a set, but now we treat them as an ordered set. We have fixed the linear order on the set of isomorphism classes of simple A modules. And this order is the crucial part in our input datum. So we denote this order by less than or equal to. In reality, we will usually take the standard order on the set of indices of our simple modules, just for simplicity. So now the definition of a standard module. So given an algebra A and our fixed linear order on the set of isomorphism classes of simple A modules, for each I from 1 to m, so these are the indices of our simple modules, we define the corresponding standard module delta I as follows. So delta I is defined as the quotient of the indecomposable projective cover of Li, which is Pi, by the trace in this module Pi of the projective module Pi plus 1, direct sum with Pi plus 2, direct sum and so on, direct sum with Pm. So we take in Pi the trace of all projectives with strictly bigger indices, and we factor this trace out. The outcome is the standard module for this vertex I. The trivial example, if I is equal to m, then there are no projectives which are bigger than m. So we take a trace from the 0 module to Pm, that's the 0 trace, so our delta m is equal to Pm. The maximal index m, the standard module, is just the projective module. Here is an example. Let A be the path algebra of the following quiver. We have 4 vertices 1, 2, 3, and 4, and we have 3 arrows from 1 to 2, from 3 to 2, and from 3 to 4. Here are the indecomposable projective A modules. The indecomposable projective P1 starts from 1 and goes to 2, so it's one-dimensional at the vertices 1 and 2, with the identity map between them, the rest is 0. There are no arrows starting at 2, so P2 is isomorphic to L2, to the simple module concentrated at the vertex 2. P3, from 3 we can go to 2 and to 4. So our projective module is one-dimensional at the vertices 2, 3, and 4, with the identity arrows between the corresponding vector spaces, and it's zero-dimensional at the vertex 1. And P4 is L4, the simple module, because there are no arrows coming out from the vertex 4. And now we can compute the standard modules for the natural order and simple modules. So we fix the natural order, 1 smaller than 2, 2 smaller than 3, 3 smaller than 4. And then we have the following standard modules for this order. The standard module delta 4 is the same as P4. This we already computed on the previous slide. The standard module delta 3, we should take P3 and factor out the submodule generated by the trace of P4. So this kills this vertex, the fourth vertex. And now we have a module which is one-dimensional at the vertices 2 and 3 with the identity map between them. And then this map should be 0 because that's a 0 map. To define the standard module delta 2, we take P2, which is simple, and factor out the trace of all bigger projectives. But there is nothing in the bigger vertices, there is nothing to factor out. So delta 2 is equal to P2. And finally, delta 1, we take P1, which lives at the vertices 1 and 2, and we have to factor out the trace of P2, P3, and P4. There is nothing in the vertices 3 and 4, but then there is this thing in the vertex 2, we factor it out, and what remains is just the simple module at the vertex 1. So these are the standard modules for this algebra with respect to the natural order. Let us now discuss properties of standard module. Property 1. Each delta I is indecomposable. In fact, it has simple top Li. Proof. Recall that the indecomposable projective cover Pi of Li has simple top Li. Therefore, the quotient of delta I also has simple top Li, provided that this quotient is non-zero. But Li, of course, doesn't appear in the top of projectives indexed by higher indices. So when we take our trace to define delta I, we cannot cover the top constituents Li in our Pi because it doesn't appear in the top of any projective Pi plus 1, Pi plus 2, and so on, Pm. So this trace actually belongs to the radical of Pi, and so the quotient is non-zero. And this proves property 1. Property 2. If some simple module Lj appears as a subquotient in the composition series of delta I, then j is less than or equal to I. Moreover, Li appears in delta I with non-zero multiplicity. Proof. Any subquotient Ls where s is greater than I will be in the trace of Pi plus 1 and so on Pm in Pi because this s appears among I plus 1, I plus 2, and so on M. And so it will be factored out from Pi when we define delta I, so any such subquotient Ls cannot appear in delta I. And this implies the first claim. And the second claim follows from our proof of property 1, where we proved that delta I has simple top L. I. So Li appears in delta I with non-zero multiplicity. Property 3. The matrix of composition multiplicities of Lj in delta I, where I and j run from 1 to m, this matrix is lower triangular with positive numbers on the diagonal. That follows directly from property 2. The only simples which appear in delta I correspond to j which are less than or equal to I, and Li appears with non-zero multiplicity. That's exactly it. And property 4, if we have a non-zero homomorphism from delta I to delta j, then I is less than or equal to j. Proof. We know that Li is a simple top of delta I. So if we have a non-zero homomorphism from delta I to delta j, this non-zero homomorphism should send the top of delta I, which is Li, in a non-zero way to delta j. And this means that the composition multiplicity of Li in delta j is greater than 0. And so the claim follows directly from property 2. Here's an example, just an extension of the previous example. In the previous example, we looked at the path algebra of the quiver with vertices 1, 2, 3, 4, an arrow from 1 to 2, and arrows from 3 to 2 and from 3 to 4, with respect to the standard order. And we computed that the standard modules are the following modules. Delta 1 is just L1, delta 2 is L2, delta 4 is L4, and delta 3 has simple top L3 and simple socle L2, and the identity map between them. And so we can compute this matrix of composition multiplicities of Lj and delta I. Since delta 1 is L1, this means that the first row is just 1, 0, 0, 0. Delta 2 is L2, the second row is 0, 1, 0, 0. And delta 4 is L4, means the fourth row is 0, 0, 0, 1. From our description of delta 2, we see that the second row is 0, 1, 1, 0. So the diagonal 1 corresponds to this, to the top of this module, and this 1 below the diagonal corresponds to the simple subquotient L2 of delta 3. And we can also note here that the only non-trivial homomorphism between standard modules is the homomorphism from delta 2 to delta 3, which basically corresponds to the fact that in delta 3 we have delta 2 appearing as the simple socle. Okay, so this was about standard modules, and now we have to do exactly the same thing for the dual notion of a costandard module. So we start with the notion of a cotrace and cotrace kernel. Let A be a finite dimensional associative unital algebra over an algebraically closed field K. Let M and N be two finite dimensional A modules. Definition: the cotrace kernel, the OTK sub M of N, of our module N in the module M is the submodule of N given by the intersection of the kernels of all possible homomorphisms from N to M. For example, if we take M to be the zero module, then all morphisms from M to N are zero, and so our intersection of the kernels is N. The cotrace kernel in the zero module is the whole of N. Example 2. If we take as M the injective cogenerator of A mod, then for any module N, the cotrace kernel into the injective cogenerator will be 0, and that's because N embeds into its injective envelope. So we can always, for any simple subquotient of N, we can find a homomorphism into an injective module which is non-zero on that simple subquotient. And so the intersection of all kernels will be 0. Okay, now let us describe the cotrace kernel in an injective module. So let I be an injective A module. What we want to understand the cotrace kernel of some module N in this injective module I. So let X be the set of simple A modules which appear in the socle of I. In other words, A simple module L belongs to X if and only if the set of A homes from this module to I is non-zero. For an A module K, denoted by K upper X, the maximum submodule of K, such that it doesn't have any simples from X as composition subvectors. Note that if we factor Kx out of K, we will get a module such that the multiplicity of any L in X in this module coincides with the multiplicity of L in the original module K. And by definition, K upper X is the maximum submodule of K with this property. So we claim that the cotrace kernel of N in our injective module I coincides with N upper X. Let's prove this. Let L be a simple module in X and E a primitive idempotent in A, such that E times L is not zero. Then the indecomposable injective module, which is the dual of the right projective EA, is a direct summand of I. If V is a non-zero element in N such that EV is equal to V, then we have a morphism from N to this injective EA dual, and hence also to I, because I has EA dual as a direct summand, that sends V to the socle of our injective EI dual in a non-zero way. In other words, the cotrace kernel of N in I belongs to the kernel of this homomorphism. And so, by the definition of the cotrace kernel, it also belongs to the intersection of the kernels of all such homomorphisms. And of course, the intersection of such kernels is clearly contained in N upper X, because every simple subquotient which is in X, we can send in a non-zero way to I. So intersection of the kernels is contained in N upper X. On the other hand, any simple in the socle of the quotient of N by this intersection clearly belongs to X. And therefore, this intersection coincides with N upper X. Here's an example. Let A be the path algebra of the following quiver. We have the vertices 1, 2, and 3, an arrow from 2 to 1, and an arrow from 2 to 3. Here are the indecomposable injective A module. The indecomposable injective at the vertex 1 is one-dimensional at the vertices 1 and 2, and with the identity map between these, and zero-dimensional at 3. That's because the only path which terminates at 1 is the identity path at 1, and the path from 2 to 1. There are no arrows coming into 2, so I2 is equal to L2. And for I3, we have a path from 2 to 3, so I3 is one-dimensional at vertices 2 and 3 with the identity map between these vector spaces, and zero-dimensional at the vertex 1. Consider as N the indecomposable projective module P2. This module is one-dimensional at all vertices, with the identity maps representing the actions of the arrows. That's because from 2 we have the trivial path to 2, we have an arrow to 1, and an arrow to 3. So now we can compute the cotrace kernels of N in the injectives I1, I2, I3, and the sum of I3 and I1. If we start at N and try to see for maps into I1, then we can kill the third vertex, and then we have the projection. And that's it. So this means that our cotrace kernel is the kernel of this homomorphism, so it's the simple module L3. So for I2, the only way to go to I2 is to kill the first and the third vertex. So the cotrace kernel for I2 would be L1 direct sum with L3. So the cotrace kernel for I3 is L1 similarly, and for I1 direct sum with I3. So we have a map onto I1 with kernel L3 and a map onto I3 with kernel L1. The intersection of these kernels is 0. So our cotrace kernel here is the 0 module. Now we can define costandard modules. Let A be a finite dimensional algebra, and let L1, L2, and so on Ln be a full and irredundant list of representatives of isomorphism classes of simple A modules. Just like for standard modules, this means that we have fixed the linear order on the set of isomorphism classes of simple A modules. This linear order is a very essential part of our setup. So now we can define the corresponding costandard modules. So they are defined for the pair consisting of our algebra A and our fixed order on the set of representatives of isomorphism classes of simple A modules. So our nabla I, the costandard module for an element I, and this is an indexing element for simple modules, our nabla I is defined as the cotrace kernel from the indecomposable injective corresponding to our index I into the direct sum of indecomposable injectives corresponding to all higher indices, I plus 1, I plus 2, and so on, all the way up to n. For example, if we take as I the maximum index m, then the subscript in the cotrace kernel disappears, it becomes a zero module, and so the cotrace kernel into the zero module becomes just the indecomposable injective. So nabla m is equal to im. Let us do an example. Let A be the path algebra of the following quiver. So we have the vertices 1, 2, 3, and 4, and we have the following indecomposable injective A modules. So I1 is simple because there are no arrows coming into 1. I2, we have arrows coming into 2 from 1 and 3. So I2 is one-dimensional at the vertices 1, 2, and 3, with identity maps between the corresponding spaces, and zero-dimensional at the vertex 4. I3 is L3 because there are no arrows coming into 3. And for I4, so we have 4 and an arrow from 3 to 4. So I4 is one-dimensional at the vertices 3 and 4, with the identity map between them, and it's zero-dimensional at the vertices 1 and 2. And now we can compute for the natural order 1, 2, 3, 4 on simple modules the corresponding costandard modules. So nabla 4 is I4, we know this from the previous slide. I3 is simple, so nabla 3 will be just I3. Now I2 and nabla 2. So in I2, we should forget everything, so we should take the maximal submodule, which doesn't contain anything from higher vertices. So we have a morphism from I2 to I3, which sends the scale at the vertex 3 to I3, and the kernel is exactly this part at the vertices 1 and 2. So I2 is concentrated at the vertices 1 and 2 with the identity map between them and one-dimensional spaces at these vertices, and it's 0 outside. And I1 is simple, so nabla 1 is equal to I1. Let us now discuss properties of costandard modules, and this will be a pure analogy with standard modules. So property 1, each nabla I is indecomposable and in fact has simple socle Li. So recall that the indecomposable injective envelope of Li has simple socle Li. So therefore, any submodule of this indecomposable injective envelope must have simple socle if that submodule is non-zero. So we only need to show that this Li is in the kernel of any homomorphism to any I plus 1, I plus 2, and so on, Im. But that's clear because Li doesn't appear in the socle of those injective modules. So this means that the cotrace kernel contains the socle of II, and so it is non-zero. And this implies our property. Property 2. If Lj appears as a composition subquotient at some nabla I, then j is less than or equal to I, and indeed Li appears as a composition subquotient of nabla I. Proof. If we have a subquotient Ls where S is greater than I, then this subquotient appears in the socle of I plus 1 and so on Im, and so we can map it to the socle of one of those injectives. And so this Ls cannot be in the cotrace kernel. And this exactly implies the first claim. And the second claim follows from the fact that we already established that nabla I has simple socle Li. Property 3. The matrix of composition multiplicities of Lj's in nabla I's, it's a lower triangular matrix with positive numbers on the diagonal. That follows directly from property 2, similarly to standard modules. And property 4, if we have a non-zero homomorphism from nabla I to nabla J, then I is greater than or equal to J. Indeed, we know that nabla J has Lj simple socle, so if you have a non-zero homomorphism from nabla I to nabla J, the socle must be covered, which means that Lj should be a composition subquotient of nabla I. And then the claim follows from property 2. Now let us look in more details at the last example. So we have the path algebra of the quiver with vertices 1, 2, 3, and 4, and arrows from 1 to 2, from 3 to 2, and from 3 to 4, with respect to the standard order. We have the corresponding costandard modules. Nabla 1 is L1, nabla 3 is L3. Nabla 2 has L2 in the socle and L1 in the top, and nabla 4 has L4 in the socle and L3 in the top. So we have the corresponding matrix of composition multiplicities. So nabla 1 is L1, so the first row is 1, 0, 0, 0. Nabla 3 is L3, so the third row is 0, 0, 1, 0. Nabla 2 consists of L1 and L2, so the second row is 1, 1, 0, 0. And nabla 4 has L3 and L4, so the last row is 0, 0, 1, 1. So we have this lower triangular matrix, and we also see that the only non-trivial homomorphisms between these nablas, so we can project nabla 2 onto nabla 1. This corresponds to this appearance of L1 in the top of nabla 2. And we can project nabla 4 onto nabla 3. This corresponds to appearance of L3 in the top of nabla 4. Here are some extra problems and questions. Number 1. Let M be an A module such that the trace from M into the left regular module A is equal to A. Show that M contains as a direct summed a projective generator of A mod. Problem question number 2. Is it true that the functor of taking trace from some module M is an exact functor for any M? Problem question 3. Compute all standard and costandard modules with respect to the natural order of the path algebra of the following quiver. So we have 4 vertices, 1, 2, 3, and 4, and 4 arrows, from 2 to 1, from 2 to 3, from 2 to 4, and from 3 to 4. Problem question 4. Prove that delta I is the maximum quotient of Pi, whose subquotients are of the form Lj, where j is less than or equal to I. And problem question 5. Prove that nabla I is the maximum submodule of II, whose subquotients are all of the form Lj, where j is less than or equal to I. Thank you very much, and see you next time.